Okay, page 8 solutions of properties of curves. Number 3. At what point of x does a quadratic function ax squared plus bx plus c have a stationary point? Under what conditions is the stationary point a local maximum or a local minimum? Even though this is not a function with numbers, a, b, and c, you can treat as numbers. So first thing we're going to do, as usual, is to take the derivative. By finding the derivative and setting it equal to 0, we can find the stationary points. So we'll have we'll have 2ax plus b. C goes away because it's just a constant. Derivative of a constant is 0. So we set it equal to 0. And so when is this equal to 0? The only thing we can vary is x. A and b are just numbers, so we can't vary those. So for what value of x will this equal to 0? So we're just going to do algebra. Subtract b from both sides. We'll get 2ax equals negative b. Then we divide both sides by 2a. And then we get x equals negative b over 2a. That looks familiar. X equals negative b over 2a. That is the axis of symmetry. It is the x-coordinate of the vertex. Is that surprising that the x-coordinate of a vertex for a quadratic is the stationary point? Okay, so, and is it a local minimum or a local maximum? Well, that depends, right? If you take the second derivative, you're going to find out whether it's a local minimum or a local maximum. So let's do that. We're going to take the second derivative and we'll get 2a. So we'll set that equal to 0. And it's never equal to 0, right? But when is it greater than 0 and when is it less than 0? Remember, the second derivative, if it's positive, it is concave up. And if it's negative, it's concave down. So we can see that if 2a is greater than 0, then it's concave up. And if 2a is less than 0, then it's concave down. So now this already confirms something we know. We know that if a is positive, that the parabola turns up. And we know that if a is negative, the parabola turns down. So using derivatives, we discover something that we already found out through experimentation with Desmos, right? So if a is greater than 0, then it's a minimum. And if a is less than 0, then it will be a maximum. So those are the other two things that we're trying to find out here. Number 5. Now we have the cubic function. And it says it has a local maximum at x equals negative 4. Find a. Okay, so now we can, where does it have a local maximum? Again, we're going to take the derivative. So we have 2 times 3x squared, that's its time sign, plus 2ax minus 24. Okay? And this can be simplified to 6x squared plus 2ax minus 24. And you can set that equal to 0, and then we're going to find the stationary point. We already know that one of the stationary points is x equals negative 4. So knowing that, maybe we can figure out what a is. So we're going to put x equals negative 4 in here. 2a negative 4 minus 24. And we're going to simplify that. We're going to get 6 times 16, which is 96. And then minus 8a minus 24. 96 minus 24 is 72 minus 8a. And so now we want to know, when does that equal to 0? So it's going to be 72, 8a equals 72. So when a is equal to 9, then we have a critical point. Okay? And just to confirm, we could, once we get a equals 9, then we could take the second derivative and then make sure that it's concave up. So we could go, oh, it's 12x plus 2a, which is 2 times 9, which is 18. And so we'll say, okay, when, let's see, x equals negative 4, what does that equal to? So we'll say 12 times negative 4 plus 18. It's a negative number, which means it's concave down, which means it is indeed a local maximum. Okay, number 7. Consider the function x times log x. For what values of x is f of x defined? Okay, now remember log kind of looks like this. Okay, so it's not defined for values 0 and less, x equals 0 and less. So it's, at minimum, we're going to say x has to be larger than 0, because that's the way log is. And we'll continue here and see if that's true for everything. Show that the global minimum value of the function is negative 1 over e. The global minimum value of the function. That is, let's see, there's no domain here. I'm not sure what they're asking here. Anyway, we're going to take the derivative as usual, okay? So they want to know the global minimum, so we do need to take the derivative. This looks like the product rule, right? So if u is x and v is log x, then u dashed is equal to 1 and v dashed is equal to 1 over x. So let's, the product rule is u dashed times v plus u times v dashed. And that equals log of x plus 1. So that is the derivative. When does this equal to 0, if at all? So basically that's saying, when does log of x equal to negative 1? What if we took e to the both sides? So e to the log x, e to the negative 1, and that equals to x equals 1 over e. Oh, and it's, 1 over e. And then, so that is the value of x, which gives a, what do you call it? And then, stationary point. So what value do we get out of f if we put in 1 over e? And it will be 1 over e times the log of 1 over e. So log of 1 over e would be, let's see, log of 1 over e would be negative 1, because e to the negative 1 is equal to 1 over e. Okay, take the log of both sides, you'll get negative 1. So negative 1 over e. And there we just have our answer. Okay, now it kind of makes sense to me. I thought about it for a while. And if you graph x log x, you get a kind of a weird function. It looks probably something like this. It's like, I don't know what it starts at, but it'll like go down and then go up or something like that. So, I think. Yeah. So it'll be like, it'll look kind of like that. So the point that we found is this point right here. Okay? So this is the y value, and this is the x value. Number 9. The cubic polynomial, blah, 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 touches the line with equation y equals 9x plus 2 at the point 0, 2 and has stationary point negative 1, negative 7. Find the function. Okay. Okay, so first we want to take the derivative because we always want to take the derivative. Let's just take the derivative so that we can use it later. 3ax squared plus 2bx plus c. And it says it has a stationary point at -1, -7. So we know that if we put -1 in here, we get 0. If we put -1 here, and oops, for a, for x, if we put -1 here, and if we put -1 here, then it's equal to x. Plus, we also know that the p-value is going to be -7 when we put -1 in here. Okay. And plus we know something about this equation here. It touches the line with the equation y equals 9x plus 2 at that point. So we know, at the point 0, 2. So we know that if we put, and this is another p dash, if p dashed at 0 is going to give us 9, because we know that it touches the line 9x plus 2. The gradient is 9 at 0. So if you put 0 in for p dash is here, then this term becomes 0. This term becomes 0. You're just left with c. So we just found out that c is equal to 9. Okay. So let's see. Now that we know c is 9, I think that's going to help us with this here. We're going to have 3a, -1 squared is 1, plus 2bx, which is minus 2b, and then we have c is 9, so plus 9 equals 0. Okay, so that's one equation with two unknowns. And then here we can also put that c is 9 here. So we know that, and I think we can figure something out with this too. It says that at the point 0, 2, it's this. So we can put p0 is equal to 2, and we're going to put zeros in for x, so that's all these become x, and then, oh look, we can find out that d is equal to 2. So we know that d is equal to 2 also. So now that we know that, let's see what can we write here. We have -7 equals -a plus b plus 9 plus 2, which is 11. So now we know a minus b is equal to 11 plus 7, which is 18. A minus b equals 18. A is equal to 18 plus b. So we can put that over there. We can put 3 times we have a equals 18 plus b, right? 18 plus b minus 2b plus 9 equals 0. 3 times 18 is about 54. 54 plus 3b minus 2b plus 9 equals 0. So that's b plus 54 plus 9 is 63 equals 0. So b is equal to -63. Okay, now that we know that b is -63, can we find out what a is? We sure can. Because if we know that b is equal to -63, then we know that a is equal to 18 minus 63, which is about 45? -45? Okay. So now we know a is equal to -45, b is equal to -63, c is equal to, and I don't need to write c is equal to -63 again. We already have that written. So I'm just going to highlight all these places. A, B, C, and D. Okay? Alright. So we have figured out P. P, and I'll rewrite it here. A is -45. B is -63. C is 9, and D is 2. Show that this function has a local maximum when x equals pi over 4. So, again, we're going to take the derivative. So this is a product, so we're going to make this u and this v. And we're going to have u dashed, which is equal to negative e to the minus x. And we're going to have v dashed, which is cosine of x. And then the whole thing multiplied by 4, right? So we're going to have 4 times u dashed times v, which is sine x. And then plus u, which is 4 e to the, oh, not 4 because we factored out the 4, e to the minus x times cosine x. And so this is the derivative. And we set it equal to 0 to find out when the maximum or minimums are. And we already know, it says, that there's a local maximum when x equals pi over 4. So it says to show that. So we could just put in pi over 4 now. X equals pi over 4 into here. And then we should show that this is actually equal to 0. We probably don't know the math to figure this out, without their hints. So, but it's a lot easier just to prove that what they gave us is true. Pi over 4 plus e to the minus pi over 4 cosine pi over 4. Okay. So now let's see, sine of pi over 4 and cosine pi over 4 are equal to 1 over square root of 2, or square root of 2 over 2. So let's rewrite this. So, and negative e over pi over 4, let's see. So we'll have negative square root of 2 over 2 e to the minus pi over 4 plus square root of 2 over 2 e to the minus pi over 4. So now we can factor out a e to the minus pi over 4. And then you can see that the 2's cancel with the 4, leaving a 2 there. And square root of 2 e to the square root of 2 minus square root of 2. So now we have a 2 here, and we also have square root of 2 minus square root of 2, and then we get 0. So we can plug in their value, x equals pi over 4, into our expression for the derivative, and we indeed prove that it's equal to 0. Now, if they didn't give us this number here, we probably don't know how to figure that out using algebra. Okay? So that's why they didn't ask us to figure that out. Consider the function x minus log x. Show that the graph of y equals f of x has a local minimum and that this is only the turning point. Show that the graph of y equals f of x has a local minimum. Okay, so what do you know? We're going to take the derivative again. So the derivative is 1 minus 1 over x, right? Show that the graph of the function has a local minimum and that this is the only turning point. Okay, so when is this equal to 0? This is equal to 0 when 1 equals 1 over x, so x equals 1. When x equals 1, there's a stationary point. Okay, and it's the only stationary point. Okay. B, hence prove that log of x is less than or equal to x minus 1 for all x greater than 0. Let's see. So if we know that this is our local minimum, So if we graph this, then this is going to be always this expression, x minus log of x, is always going to be greater than its value. Yeah, so we could say something like this. We could say the function is greater than or equal to its value at x equals 1, right? Because this is the minimum point. Okay? Oh, and if we want to prove that this is the minimum, then we could take the second derivative, and we know that the second derivative of this is going to be negative 1 x to the negative 2. Yeah, I think that's it. And then so we know that like whatever value of x you put in here, you're going to get a positive number. And if you get a positive number, then it's going to be concave up. And then so it is indeed a minimum. Okay, so I'm sorry, that's like completing part A. Now with part B, since we know that x equals 1 is a minimum, we can put that the function at x equals 1 is like the smallest value possible. Otherwise, the function is always greater than that. Now we're just going to substitute in the expressions for the function and for the derivative. Okay, so now we're just saying the function is, not for the derivative. We're going to plug in 1 here. So 1 minus the log of 1. The log of 1, is 0. So x minus log of x greater than or equal to 1. Because log of 1 is 0. So now we have x is greater than or equal to, add log of x to both sides. 1 plus the log of x. And now we're trying to prove this. Log of x is always smaller than x minus 1. So now we just subtract 1 from both sides, and now we have log of x is always smaller than x minus 1. Okay. All right. That's it for page 8.